I welcome you again to the UNU-INWEH public event, the Science Talks. For those joining us for the first time, welcome. We are glad you can join us today, and we say a big thank you. I am your host for today, Professor Grace Oluwasonya. Before presenting our distinguished speaker, please know that there will be an interactive Q&A session at the end of the presentation. At that point, there will be room for comments, Q&A, and any other contributions. Please type your questions or comments in the Q&A chat box. We will pick them up from there. Thank you. Also, videos of all our previous science talks from 2024 to date are available on demand on our YouTube channel at https://unu.edu.science-talks with an S. The topic of today's talk is NASA-ISRO Synthetic Aperture Radar, acronym NISAR, imaging radar unveiling the changing Earth. So let's talk. Our presenter is Professor Carl McDonald. I hope I got that correctly. Professor Carl is the co-lead Research, Development, and Innovation Pillar at the UNU City College of New York, USA. He's also the Terry X Professor in the Department of Earth and Atmospheric Sciences, Director of Sustainability in the Urban Environment Graduate Program at the same university. Before I focus on his area of specialization, he is a member of the NASA-ISRO Synthetic Aperture Radar science team. He had previously worked as a principal scientist, in fact, for about 2 decades, at the Jet Propulsion Laboratory, popularly known as JPL, California Institute of Technology. Now, he's an academic part-time scientist in the Biosphere Group in the JPL Science section. Before you start to hear the brief grammar in terms of imaging radar unveiling the changing Earth, I want to break down his area of specialization to say he uses satellite technology that utilizes microwave signals. Microwave signals are those that can see through clouds and work both day and night to study land ecosystems. By this we mean forests, grasslands, and soils, and frozen environments such as snow, ice, and permafrost. It looks at all these environments, how these environments change with seasons. In other words, when snow melts or when soils become wetter or drier, to explain how healthy ecosystems are and how water moves through the environment and how carbon is stored and released. Summarily, it uses satellite data to track seasonal environmental changes and understand how land, water, ice, and ecosystems affect the Earth's climate and water systems. So for those who may not follow the big grammar, I believe you have basic understanding of what Professor Carl, has been doing. And now I'll yield the floor to Professor Carl McDonald. Carl, the floor is yours. Let's go.
Well, thank you very much for that introduction. I'm happy to be here today. I'm going to be talking about the NASA-ISRO Synthetic Aperture Radar mission. I've been working on the science team for the last several years. If anybody's familiar with this mission, it was actually planned for launch some time ago, but there were several things got in the way concerning COVID and things that sort of happened after that. But it did finally launch this past summer. It's a large imaging radar instrument, the first of its kind, in that it's flying two frequency radar for studying the changing Earth environment. I'd like to go over what some of the science objectives are and some of the unique capabilities that this mission's providing in terms of Earth observations and remote sensing. We're all very excited about it on the science team. Let's see. Okay, so the partnered mission is between NASA and the Indian Space Research Organization, ISRO, with each of the institutes contributing various parts of the mission. We finally launched in July of last year from India. That was part of the Indian Space Agency's contribution to the mission, was they provided the launch. This is a rendering of the satellite that you see here. The main electronics package is housed in this cylindrical structure here that's merged to the bus, to the spacecraft bus, and this is a large reflector dish. The radar transmit receive modules are located down here, and they use this reflector dish to guide the radar views of the Earth. The mission has key science objectives that are focused in three basically different science areas. One is cryosphere focused, in that we're looking at the dynamics of ice sheets, Earth's great ice sheets, Greenland and Antarctica, and also glaciers, and links between those components and climate change, and how that's merging in with sea level. In terms of ecosystems, which is the focus area that I'm emphasizing in my research, we're looking at understanding the dynamics of carbon storage. We're looking at landscape disturbance. We're looking at wetlands inundation dynamics, and we're looking at agriculture. And also we're providing some unique capabilities for looking at standing biomass in terms of carbon stocks as they're distributed around the planet. The solid Earth component of the mission science is looking at focusing on studying earthquakes, plate tectonics, volcanic activity, things like landslides, and those sorts of hazard responses. So we have three very different science threads, and there are science team members that are focused in each of these areas. There's also some key applications objectives, which I think come in very useful in the context of the United Nations University. And there we're looking at understanding the societal impacts of the dynamics of water, the carbon cycle, sequestered CO2 reservoirs, restoration of ecosystems, monitoring degradation of ecosystems in terms of science applications and how those link to societal needs. The agricultural monitoring capability is to look at food security objectives, looking at things like how actively farmland is being managed, what is sitting dormant, what is growing crops for food consumption, and those sorts of things. And then there's also an urgent response component of the mission, looking at things like oil spills or hazards related to storms or earthquakes and things of that sort, where the mission can actually be tasked with targeting responses as they occur. We have a capability to collect extra data and then get those to a user community. And I think that's a very powerful component of this mission as well. Looking at the instrument itself, it consists of components that were provided by NASA and by the Indian Space Research Organization, ISRO. In terms of the payload, NASA has provided an L-band radar instrument. That's a radar that operates at about 23 or 22 centimeters wavelength. ISRO has provided an S-band radar, which is operating at about half the wavelength, about 12 centimeter wavelength. So we have a dual frequency radar capability, and each space agency is downloading and assembling their respective data sets. And then those are transmitted to a central repository available through data archiving schema that are merged with Amazon Web Services. So this mission will provide an enormous volume of data. It's measuring all of Earth's land surfaces, plus the ice sheets and sea ice on a 12-day repeat cycle. And so it's recording several terabytes of data downlinked per day. It will provide more data than all of NASA missions combined in the past. So it's moving NASA into a big era of large data distribution and assembly. All these data, by the way, I should point out, are publicly available. There is actually some data now that's publicly available through the Alaska Satellite Facility managing the Amazon Web Services buckets, where we have some of the data released now. Why we want to use radar and some of the unique capabilities of radar. This is a chart that shows some of the more recently implemented imaging radar missions operating across various components of the microwave spectrum. NISAR is here, and it has an L-band and an S-band system. There have been radars flown by the Japanese Space Agency, by the Europeans and other partners. The Canadians have the RadarSat constellation that they work with. But we're working in this microwave area of the spectrum, which provides a nice capability owing to this atmospheric window. This is atmospheric opacity here. Opacity is basically dropping to zero. The atmosphere is transparent in the bands where these radars work. So we can get a very consistent time series capability, not obscured by clouds. So we get nice time sequence data that allows structuring of repeat pass observations to allow the capability to detect and monitor change in the environment. The reason we want to use different wavelengths here is because owing to the scattering physics, the interaction of the radar energy with the various vegetation land cover types, you get different sorts of penetration capability. The longer wavelength L-band radar energy will penetrate vegetation more so than the shorter wavelength S-band. S-band will be very useful looking at lower biomass vegetation structure, things like agriculture and things of that sort. It also has a very unique capability here for providing 12-day repeat observations globally with sub-cycle samples within those 12 days, and collecting both polarimetric radar data, where we can look at the polarization effects of radar scattering for doing ecosystem monitoring and those sorts of things. But because of the consistent temporal repeat, we also have implemented this interferometric radar capability to look at developing interferograms and on a 12-day repeat basis to look at surface deformation and change in that regard. This is a little diagram about one of the unique features of NISAR, which allows it to give us such nice temporal repeat coverage, a technique called SweepSAR, where the radar transmitters illuminate the reflector dish, eliminating the entire area observed by the radar across the radar swath. And then on receive, the radar beam is steered to focus on different areas of the swath as the radar signal returns. So on transmit, the radar illuminates the entire swath of interest, and on receive, the beam is steered in fast time to follow the echo as it returns. This reduces ambiguity in the radar and the radar scattering in terms of assembling the radar images, and allows us to look at a very wide swath area to give us global coverage every every 12 days in this case. This is a photo. You get an idea for the size of this, the instrument being assembled in the clean room at the Jet Propulsion Lab. This is the cylindrical structure. These are the radar transmit receive modules, antennas that sit here. And this, for scale, you can see the technician working inside the cylindrical structure, so you get an idea of the size of this. And this is the instrument, which was, as it was being prepared for launch, put into an environmental chamber. The rigors of launch are simulated by shaking the instrument and simulating the launch environment that it has to go through to get up into orbit. And also it's put in a vacuum situation and heated with heat lamps to simulate the conditions, the environment of outer space. A process we call shake and bake in the vernacular. This is the way the data are being assembled and distributed. Basically, the NASA instrument, the L-band radar, are being downloaded through the NASA near-Earth network of receivers. And then those data are then transmitted into Amazon Web Services and processed and assembled at JPL and archived at the Alaska Satellite Facility Distributed Active Archive Center in Fairbanks, Alaska, through the services provided by Amazon. The S-band data are downloaded to the Indian facility, which is in Antarctica, and also into the ISRO facilities in India and Bangalore and other places. And these S-band data are then processed by the ISRO team and provided as a separate suite of data sets. The Indians do have their own science objectives. They're producing a lot of different data products specifically for the Indian subcontinent and for Antarctica. And then all the data are then merged into the joint buckets in Amazon Web Services. So all of the data will be freely available to the user community to advance research in this area and the applications needs as well. This is the observation plan. So this shows the various modes that the radar is operated in order to implement the global acquisition of data. The L-band data will be truly global in terms of observing all the Earth's land surface, including islands, Earth's great ice sheets, and also sea ice. The Indians have a little bit more of a focus of where they want to acquire S-band data. They are focusing S-band acquisitions in the Indian subcontinent and these regions in South Asia and also over Antarctica. So the S-band data is not acquired globally, but it is also, along with those two regions, providing data over the network of ecosystem calibration validation sites, which are distributed globally. And so those areas will give us some very unique opportunities to look at dual frequency observations and understand how those can be beneficial. So the data analysis and archive approach that we have from the NASA side is basically we're producing a series of level 0 through 2 products, which will be global in scope. And these will include the radar observations themselves. So we're going to get the interferometric SAR and the polarimetric SAR data assembled through level 2. Then at level 3, NISAR has kind of a unique approach here, where commonly NASA missions produce global maps of certain variables that they're tasked with providing. NISAR has too many sorts of potential products it could produce. So it's going to produce some limited products, but it's going to validate the capability for the science tasks over the calibration validation sites and exercise things like Jupyter Notebooks tools that will show, that will be able to ingest the data. Then the user community will be able to take these Jupyter Notebooks or their own tools of interest to look at any, deriving any parameters from the level 2 products that NISAR then would provide. So these would include things like derivation of woody biomass and vegetation structure, looking at vegetation disturbance, deforestation, fires, these sorts of things. Wetlands inundation area and inundation dynamics over inundated wetlands. Also assessment of crop area and active cropping area. And from the interferometric radar side, we're looking at ground deformation and rate changes in ground deformation, looking at change proxies for looking at things like damage mapping and things of that sort. Ice sheet velocity and glacier velocity, so the speed at which glaciers are moving and the rate at which the great ice sheets are changing as well. There's also an experimental vegetation structure component that is combining both the polarimetric capability and the interferometric SAR capability. Now, the Satellite Needs Working Group, which is an organization that NASA has assembled, an advisory group basically, is looking at, has tasked actually NISAR with producing a soil moisture product globally. So this will be available at about a 200-meter resolution globally, except in the Sahara Desert where its resolution isn't so important. So that's at about 400 meters. The rest of these products will be able to be generated at about a 20-meter resolution. So we're looking at a pretty high resolution capability on the order of what you're used to with Landsat. The global products are a little bit coarser resolution. And then another thing we're involved with is another task that the Satellite Needs Working Group has identified, and that's looking at global surface water extent that is being produced and managed outside the project by a project called OPERA, which the surface water extent component is housed at JPL for that. Also, a global disturbance product will be produced. And in terms of North America, there's a deformation product, which is looking at things like landslides, plate tectonics, volcanoes, things of that. And that part of this is managed outside the NISAR project proper. And the way this satellite works, basically, is a little animation here. It uses the motion of the satellite to build up a time history of radar pulses over a common area. This is putting it a little mildly. This is very technically complex, but using the overlapping nature of these sequences of radar pulse returns, an image is then built up over the area at about, we can get down to 10 meters, but what we're producing for general distribution is at 20-meter resolution for the general community. But if you're interested and you want to go back to some of the intricacies of how that product is assembled, it is possible to get down to a higher resolution with some trade-off considerations. So basically for radar interferometry, we've got the technique is that you're using a time sequence from time 1 to time 2 of 2 SAR observations of an area. And since SAR is a coherent sensor, you have a coherent phase front that's transmitted and scattered back from the target. And if you look at acquisitions that are separated in time, say repeat acquisitions for NISAR will be 12 days, you can then do a little interferometric processing against one phase front and the other, and that gives you the ability to look at surface change and deformation over that time period. This is an example of what these data look like. On the left, you see a standard radar image. This is what the polarimetric data will look like, basically grayscale with one grayscale channel associated with each polarization that the satellite will be monitoring. And on the right, you see the interferogram, which is an example looking at relative phase between two passes. And you see it wraps around this color bar here with one sequence in color corresponding to one cycle of relative phase change from the radar. And so it's this phase information that gives us information about surface features that may have changed between sequences of observations that NISAR provides. This allows NISAR, the combination of these capabilities makes this a very versatile instrument. Some of the applications that we're looking at in terms of what the polarimetric SAR is providing include things like flood extent, loss of land in the coastal regions, or other land degradation processes. The Indians in particular have an interest in looking at coastal bathymetry, so we can do shallow water bathymetry with this instrument. We're looking at soil moisture and biomass, mapping vegetation classes, looking at vegetation structural features, very, very valuable for looking at the biodiversity issues related to structural change, pollution and pollution impacts. SAR has been shown to be very useful at looking at oil spills, for example, as one impact of that. Water flow and degradation of systems in deltaic regions, things like that. Using the interferometric capability where we can look at land surface movements, this has applications in geophysical modeling, studying subsidence in coastal regions or subsidence because of fluid withdrawal from aquifers, for example, which actually cause a small deformation. Aquifer drawdown can cause a small deformation in the surface of the associated land above the aquifer, and you can actually measure this at very small fractions with this radar. The interferometric capability of NISAR will be able to characterize changes on the order of millimeters in terms of land change. Also looking at things like land change in flood extent and water flow through wetlands as proven useful. The requirements, I'll talk a little bit about the ecosystem side here because that's where my research has been primarily focused. NISAR was assigned a series of requirements related to monitoring crop area, monitoring wetlands extent and inundation, monitoring land cover disturbance, deforestation, these sorts of things, fire and recovery, and characterizing biomass for moderate biomass covered regions, forests and agriculture and these sorts of things. So we were given this set of ecosystems requirements, and we're working in the context of assessing right now the NISAR capability for actually meeting those requirements. That's our function as the science team. So we have assembled a global array of calibration validation sites where we are using in situ measurements, other satellite data sets, particular aircraft data in some cases, to actually get very fine scale characterization of these particular parameters across the broad array of calibration validation sites, which include the tropics, the temperate, the boreal Arctic regions. And we're exercising the retrieval algorithms that we have to verify that NISAR is able to actually meet those requirements which we were assigned to address. In addition to that, we have a network of calibration targets, these trihedrals, which some of the primary sites where these are located include Alaska and also Oklahoma. We've got an array of these which we can use to actually calibrate the radar data in terms of getting a quantifiable engineering measurement out of it. So there's two aspects there for the calibration validation. This is a little bit, I'll talk a little bit about the wetlands work here. One thing that's very unique about especially the L-band instrument, the longer wavelength radar, is it's able to penetrate vegetation canopies and see below, for example, forests to see if the state of the surface underneath the trees is actually flooded or not, or there's also a capability there to retrieve an estimate of soil moisture. And that is unique to radar. You're not going to find that capability with the optical satellites that have flown before, but it's a capability of the radar related to the physics of interaction of the radar energy with the vegetation. This is a sequence of images. This was acquired by the Japanese JERS satellite many years ago. This is one of the early L-band radars. I think the first free-flying radar at L-band that was provided. But you're looking at a river here in Brazil that is going through minimal inundation conditions and then going through an annual cycle of flood pulse that happens in the Amazon on an annual basis. We can actually measure very well these bright areas which associate with inundated vegetation. And this is all forested areas, so we're able to get a very clear delineation of the timing and extent of these sorts of inundation dynamics. We are working for our calibration validation activities for wetlands in northern Peru in the Pacaya-Samiria National Reserve. This is our wetlands CalVal site for the tropics. It's a very diverse landscape. It has a lot of different kinds of wetlands vegetation in it. And it gives us the ability to exercise algorithm retrievals for inundation extent and state in a time series fashion over a very complex array of tropical land cover. These are some pictures of what we have down there on some of our site visits that we've done. But you see the inundation at different levels through the landscape. And you notice here the watermarks on the trees. There's an annual flood pulse that moves through here, peaks at about March, April timeframe every springtime. And this is the level the water commonly gets to. So you go through this 12-month cycle going from low water, which this is, to a high water condition where this entire landscape is flooded. We've designed a ground collection scheme that will validate NISAR's ability at the 10-meter to 20-meter resolution scale relative to the flood pulse in the 1 hectare regions that we've segmented the landscape into, looking at the progression as the landscape inundates and as the inundation flood pulse retreats. We're planning this year in May to fly the NASA UAVSAR, which is a high resolution aerial airborne radar that NASA JPL flies. And we're going to underfly the NISAR satellite. So we will have coincident NISAR observations and very fine scale, high resolution radar images, along with data from in situ sensors that we have in place to look at inundation state, to do an accurate calibration retrieval of the inundation state and assess just how well NISAR does in those retrievals. The idea here, for example, in the Amazon is to look at high water and low water conditions shown here as we derived from a Japanese instrument, the Pulsar 2 instrument, for the entire Amazon basin. Pacaya-Samiria is this wetlands complex up here in the upper Amazon, northern Peru. You can see as we go from low water to high water conditions, and on an annual basis, looking at minimum and maximum inundation, there's a tremendous amount of inundation that occurs, and it's very ecologically critical. It has implications for global carbon cycle and climate cycles, and these inundation regimes are changing. But what we'll be able to get with NISAR for the first time are maps like this with a 12-day resolution to understand the dynamics of how these inundation patterns integrate with each other, effects on biodiversity, carbon cycling, climate linkages, things of that sort. We're also looking at coastal wetlands. In this case, this is a salt marsh system that's on Long Island Sound. Actually, it's not too far from where I'm talking. It's in Connecticut. These are tidal systems, which the inundation changes not only seasonally but on the lunar cycle with the tides. Looking at low tide here to high tide, we get a lot of change in inundation that occurs, but because of the NISAR sun-synchronous orbit, you're observing this at the same time every day. It takes a while to go from extreme to minimal inundation observations with NISAR, because you're not synchronized to collect data at such a high frequency as the tide changes. But we can put together models, bathymetric models, based on these time sequences to understand extreme tide events and look at things like linkages with species habitats. A lot of endangered species live in these regions, and also exchange of nutrients with the neighboring estuaries. We've got studies going on in the Chesapeake Bay, Delaware Bay, along with what we have in Long Island Sound, looking at that. In terms of biomass, we're looking at assessing biomass at areas of vegetation less than 100 tons per hectare. These are the moderate vegetation areas. The green regions shown here is what NISAR's contribution will be in terms of actually getting quantified retrievals of standing biomass. The red areas here are where we have very high biomass regions, like the tropical forests. These are being covered by a European mission called Biomass, which actually flies a longer frequency, a longer wavelength radar to get the high biomass regions. We're really concentrating on these sort of green areas and the yellow, less biomass regions. And we're working in concert with instruments such as JEDI, spaceborne LIDAR, which give us very detailed observations of vegetation structure. These are data that we acquired with a ground-based scanning LIDAR system that we built in my lab here, looking at transects of vegetation structure, in this case in the Harvard Forest in Massachusetts. And we're using data like this as calibration validation sources for the NISAR data. This is a example of forest disturbance, the different kinds of disturbance that we see as we go through a forest disturbance cycle in Brazil, looking at areas that have experienced deforestation as an abrupt change, seen here in this time step. This is an area where the landscape was degraded and the forest is slowly dying off. And this is a riparian forest that's undergoing the inundation cycles that go on through these various time steps. So we're able to assess these sorts of things. Getting into the land cover mapping as related to agriculture, not only are we looking at identifying where there is agriculture, but we can use the time sequence to look at variation in the radar signal that's associated with crop growth. And to do that, we can basically use some statistical techniques looking at time series variation to identify agricultural fields that are actively being managed and growing crops versus those that may be sitting fallow. This came up to be a of critical interest when the war in Ukraine broke out, because a lot of farmers abandoned their fields and left crops to go fallow when that happened. So we will have an ability to measure those sorts of things. And this is an example of how we can use the dual frequency L-band and S-band data to look at various types of land cover, both in some of the cash crop sorts of situations. This is an example of wheat fields in Ukraine, and also some of the more tropical sorts of agriculture situations, banana and oil palms here on the right shown. This is an example here looking at the Los Angeles basin, Southern California, of the seasonal cycle in terms of aquifer drawdown and recharge. This is derived from a long series of modeling and observational exercises, but it shows the vertical extent here is the dynamic is exaggerated a bit, but we can get to very fine scale observations of looking at surface deformation associated with that drawdown and recharge event. And we'll be able to do this. We're doing a map of the full North American realm like this that we will be building. In terms of some of the hazards, this is an image of a landslide that was acquired by the NASA airborne radar. We'll be able to look at surface deformation and disturbance associated with things like landslide events and avalanches as well. Get into some of the NISAR data that's starting to come back. This is a image of a coastal region in Maine. Let's see, and showing the features and escarpments and things in the island environments. This is one of the first NISAR images that was actually downloaded after the instrument started to retrieve some radar data, probably about 2 months after launch by the time this came down. This is in the Minnesota, North Dakota region of the upper Mississippi region, looking at some of the land cover types that we're seeing with NISAR. You see the agriculture and different pasture lands here, pivot irrigation going on here. These are some forested wetlands along the river that we're seeing. Also, there's ability to detect differences in the crops that is shown. This is corn up here. And then some of the fields here that have actually identified as fallow, showing up with a very dark backscatter. I wanted to, let's see, I've got a series of images here now from a few examples, but what I want to do, I've got those images actually projected onto a Google Earth background. We can step through and look at some of these. We're going to zoom in on the Blackwater National Wildlife Refuge along the Chesapeake Bay here. This is a sub-region of a NISAR image over this area. I had to cut it down in order to display it because the image is so large. It actually covers a vast majority of the Chesapeake Bay. But this is a reserve, large salt marsh and tidal wetland region. You can zoom in on here, and you can see some of the features here associated with where there's open water, where there is some emergent vegetation that's being exposed by the varying, as the water recedes or as it starts to cover up. And you have the boundaries here associated with where there's more developed land. As an example, this is where there's more higher biomass vegetation. You can turn this on and off, and you can take a look at what the difference is between the optical data that underlays Google Earth and what the radar data looks like. It provides another dimension of detail associated with the distribution of surface water in this area. We can go down to the tropics now Pacaya Samaria, northern Peru. This is our wetlands Cal-Val site for the tropics. We have established, this is the Ucayali River, which is one of the headwater rivers that forms the Amazon. And the Pacaya River comes along this area. So the dark areas here show open water along the river channels and these lakes. So this is a very expansive wetlands complex. What you're seeing here is a false color composite, again, between two polarizations that NISAR is recording in this area. We have established a test site right in this area where we've put a variety of in situ sensors to measure water depth in these wetland systems. And we're going to be taking a trip there in May to do some field expeditions in concert with overflights of this area with the NASA airborne radar, UAVSAR, which will be underflying NISAR in order to validate the accuracy of the retrievals of what's showing here. These different colors represent different combinations of vegetation structure and inundation state. There's a little village over here, Britannia, and this is a oil installation. This is a refinery up in this part of the reserve. And then there's a ranger station over here where we've centered a number of our studies. Show you what some glaciers look like. Let's go on up to Alaska. This is, let's see, a glaciated region of Alaska where there was actually an earthquake not too long ago, and we actually captured before and after the earthquake, and you can actually see avalanche zones associated with that earthquake. But you're looking at the glacier region here and the exit of the glacier. This is polarimetric data. This is not interferometric data. So there's the velocity is not displayed here that NISAR will be able to get to. We're still working on calibration of those data. But this is what we're seeing here, and you can switch this on and off. This is what the optical data sets are showing. You see it's pretty much saturated. You're just seeing everything is snow covered. But with the radar, you're able to penetrate through the dry snowpack and see some of the underlying structures to look at these features. And then we'll also be able to get to some of the fine details in terms of the velocity fields that link actually the mass change in glaciers to climate and things of that sort. This is the Yukon Delta up here in far western Alaska, looking here at a tundra type of environment underlain by permafrost. This is the sort of features we're seeing here. This is the Yukon River as it exits into the Bering Sea over to the left of the screen. And this is a subset of the area that's covered by NISAR, which I've shown here. And you can see the level of detail that NISAR gives in terms of variations in the morphology of the surface, what's going on along the rivers. Also, we're hoping to use these data combined with INSAR to look at degradation in permafrost fields. So that's going to be of high interest in the high north. Let's see, I'm going to call my PowerPoints back here. We looked at those. Hubbard Glacier. So there are numerous applications that we'll be able to look at, which we've gone through some of those in this case. But there's also a series of white papers that have been written by the NISAR science team looking at various thematic areas for applications NISAR to looking at societal needs and informing on things like wildfire, oil spills, land subsidence, coastal resiliency, induced seismicity. This is a issue when I guess you have oil extraction going on related to fracking and things like that. There have been, earthquakes that have occurred because of that. So that's a key thing here as well. Permafrost degradation. Also, the integrity of levees and dams is a potential to look at here. There's been a lot of work done in the Sacramento Delta, California, looking at some of the levees at risk in those areas. So with that, I'd like to wrap it up, and I'd be happy to entertain any questions you might have.
Thank you very much. Just a minute. Yeah. Thank you very much. I won't even pretend I understand half of the work that goes into this massive, in fact, very massive work that you do. But I want to start with the so what. I'm more interested in the so what angle, and also start like an Oliver Twist. So I've seen the numerous aspects, that we're covering, flood, drought, ice, and the like. Is it possible to extend this to measuring water quality of surface water?
So water quality as a direct retrievable is probably more related to a spectral signature that you would get with an optical satellite. It's not to say that these issues aren't complementary in terms of the ability of radar to help support water quality assessments. One of the things we're trying to do in tidal situations, for example, the studies we have going on here with NISAR along the Long Island Sound, is to look at nutrient exchange with the tides. So understanding residency time of high tides and the extreme nature of high tides versus extreme low tides, and linking those with a transport modeling capability that might explain some of the more direct spectral data that you get that look at water quality issues in the neighboring estuary is an area of I'm quite interested in pursuing. Actually, I've been working with some of the folks here at City College on those sorts of things. That's one thing we're trying to do. So I think there's a lot. I focused on what NISAR can do basically as a singular instrument, but there's a whole vast array of science that can be sort of unveiled as you start to merge it with other observables. And I think that is one of the key areas of contribution that we can have. Yeah, so see what else that there's also if you look at NASA's Earth science portfolio in terms of what the thrust areas are, these spheres that they have now defined for the key science objectives to be explored, there isn't any of those objectives that isn't somehow benefiting or won't somehow be benefiting from NISAR data. It's an instrument that's going to be providing information across a high degree of interdisciplinary science fields. One of the challenges we have as a radar community is that understanding radar data can be a lot less intuitive than understanding something like an optical image from Landsat. And that's just the nature of the radar scattering physics. So we're putting a lot of effort into outreach activities and educational tools that will be developed so that people will be able to ingest NISAR into their science and study things just like that.
So fingers crossed, I'll say, because one of the issue, given the cost, of accepting ambient water quality, it would be nice to have an alternative to how that can be done to give us robust water science, that can keep helping humanity. So thank you. We're hopeful that one day we'll be able to do more, on water quality with NASA. There's a question here. Timmy says, this sensor still has relatively poor temporal resolution, particularly for dynamic monitoring. What are NASA's future plans to improve temporal resolution?
What are NASA's plans to
improve temporal resolution of the
sensor?
Did you get the question? You want me to repeat it?
Well, a lot of, in terms of improving temporal resolution, NISAR is getting there. I mean, we've got 12-day exact repeat data with subcycles within that. So every 12 days, you're going to get 3 observations of every part of the land. Now, there are sensors like MODIS or SMAP, for example, which is also a microwave sensor, that provide global data every day, but they're at coarse resolution. So there's always been this trade between getting high resolution, fine scale information, and high temporal repeat observations. The advantage of radar and microwave sensors in general is that you're not going to be limited by cloud cover. So some of the more familiar instruments like MODIS, a lot of those products that are derived are interpolated products because of the issue with not being able to see the surface through clouds. And it doesn't matter how often you sample, if there's a cloud in the way, you're not going to see the land. But radar doesn't suffer from that. The European Space Agency has, of course, they have the Sentinel-1 imaging radars, of which they fly multiple versions, or the same sensor in different at different time synchronicity, so they can assemble data from different satellites and get something like a 6-day repeat observation with multiple satellites. So that's another way to attack the problem. NISAR will, I don't think they're going to build a second version of NISAR to increase the temporal fidelity. I don't think they're going to do that. They'll fly some follow-on to NISAR after this that may provide more capability.
Okay, out of curiosity, you may say, who's funding NISAR? Yeah, who is funding NISAR? The funds for the project, because the data is publicly available at the end of the day, so who is funding it?
I'm not sure. I'm sorry, you're not.
Okay, I'm asking who funds this NISAR?
Who funds it?
Yeah, the sponsors.
NASA has paid for their NASA part, and ISRO has paid for their contribution. It's funded at the agency level.
Oh, okay. Another question from the room. Yeah.
Thank you, Professor McDonald. A very, very interesting presentation. I was wondering, can you mentioned that NISAR can now monitor, cropping patterns and land use change. How do you see this data kind of influencing farmer behavior or agricultural policy or food system planning, and kind of, what needs to happen to kind of build that bridge between this level of data and use at the kind of community level?
Well, I think the kind of information that you can make available to farmers, we've worked some with that community with other sensors. First of all, they have to you have to have a value added demonstration that actually shows a farmer that it's useful for him. And of course, I'm used to some of the agriculture community I've worked with here in the U.S. They tend to be pretty knowledgeable and they have specific needs. So I think what really has to happen in an application sense is a lot of one-on-one consulting. There's a lot of opportunity to put together, say, something as simple as an app on an iPhone that provides information about perhaps an informed condition about water availability or water irrigation. In other countries, I've worked a little bit in Argentina on some of the issues, and the problem that they have there is when they provide resources with some of their farmers, which a lot of individual farmers there, they will just turn around and sell that because they're so desperate for cash that they won't take the fertilizer they're given that is informed that needs to be applied. They need cash on the table now, so they'll sell their resources off. So it's really a very society specific thing is what I've come to realize, but it requires a lot of understanding the individual needs at that level in order to get these sorts of data integrated within a decision support system of sorts.
Yeah. A quick last one before we go because we've run out of time. I'm just wondering, from your experience with NISAR and the images that it provides, how do you deal with the mistrust, of those who still believe that climate change is a myth?
How do you if I understand your problem, it relates to how do you convince people that the data are valuable in that regard? It's education, I think, is really the needed. A lot of it's political will, and so I think in terms of value of the data, I think a lot of it is it's really impingent on the earth science community to have a lot of outreach and engagement at the community level so that they can understand the issues that we're trying to address.
All right. On that note, we'd like to call it a wrap. So, Professor Carl, thank you so much for your time, for sharing your work with us. If there are more questions, we'll collate and send them to you by email, for you to answer, and to the specific requests that we have. So on this note, we say thank you to everyone who has joined in today, and we hope you'll be able to join us once again tomorrow. Next week, Wednesday, same time. Thank you very much once again, Professor.
Thank you. I look forward to visiting you sometime.
Oh, that would be so great. We look forward to having you here.
Yeah.
All right, take care now. Bye.
Bye.